Okay, so today is our great pleasure to have Professor Daniel Robinson from Lehigh University to give us a talk. So Daniel now is an associate professor in the industrial and the system of Lehigh University. So Daniel got his PhD from UC San Diego in 2007. After that, he did a postdoc, I think for 3 years, in University of Oxford and Northwestern University. After that, he joined the Department of Applied Math and Statistics in Johns Hopkins. Then he joined the Department of Industrial and Systems Engineering at Lehigh University. So his research area is primarily in optimization, with specific interest in the design, analysis, and implementation of efficient algorithms for large-scale convex and also non-convex problems, and also with particular interest in the applications related to computer vision and medicine or healthcare. So today he's going to talk about the inexact proximal gradient method with subspace acceleration. So Daniel, I'm going to give you a control.
Okay, thank you very much. So thanks for the introduction. Thanks for the invitation. Glad to be able to get a chance to talk with everybody. And the research I'm going to be talking about today is research with a couple of collaborators. One of my close long-term collaborators, Frank Curtis, who's also at Lehigh, and one of my PhD students, Yu Tong, who's in his third year right now. So the research I'm going to be talking about is about, as the title says, it's about inexact proximal gradient methods, and in particular with the addition of subspace acceleration. Okay, so I'll of course clarify what all of this means. I'm sure many of us are familiar with, in general, inexact proximal gradient methods, but fewer maybe with subspace acceleration. And I'll just say right up front that when I'm talking about subspace acceleration, it is not what people often think of when they think of, for example, Nesterov acceleration or momentum in optimization algorithms. We're talking about a different type of acceleration here that is related to certain definitions of subspaces that I'll define, and also acceleration through use of second derivative information, okay, but in somewhat limited fashion. Okay, so you don't want to use full second derivative information because that might be quite expensive. So we're going to use some limited second derivative information to lead to algorithms that are quite efficient in practice, can get high accuracy solutions when needed, and generally are, I would say, perform are more robust in general. Okay. So the overall then outline is, I'll just give a bit more of an introduction about the types of problems we've been interested in. In particular, these are different types of optimization problems that have as its key component sparsity, some kind of sparsity regularizers in them. So like the L1 norm, or in our case, we're going to focus mostly today on group versions of that, such as like group L1 type of regularizers. So the first, after that brief introduction, I'll talk about a method that it's been accepted for publication. We started working on it probably a little over, maybe even about 2 years ago, but it's a second order method, and it's going to be built upon exact use of proximal gradient calculations. Okay, so I'll discuss those details, but importantly, it's based on exact proximal gradient calculations, which means it's applicable to things like L1 norms, and it's also applicable if you have group norms, as long as the group of variables, how they're sort of grouped together, are non-overlapping. Okay, but the problem is, I mean, that's algorithm is fine, but we've also been interested in some problems where the groups are overlapping. Okay, so the sort of the different groups of variables can have overlapping. So one variable can belong to multiple groups at the same time. And in that case, the computation of what's called the proximal gradient step or iterate, there's no closed form solution for it. So that means that the fact that we've built this algorithm upon exact computation of the proximal gradient means that it's no longer going to be reliable or applicable, and certainly have no theory for that method working. Okay, in that case, in the case that the groups are overlapping. So we tried it and it didn't work particularly well. So that led us to then want to consider how can we deal with inexact computations in these types of methods. So then the next main part of the talk is going to be taking a step back and just saying, okay, how can we deal with inexact proximal gradient calculations to develop an algorithm? Okay, and there has already been some work done on that, but we're going to look at it again, this problem, and we're going to be looking at it sort of keeping in mind that our ultimate goal is really to build a second order method that uses inexact proximal gradient calculations. That's our ultimate goal. So keeping that goal in mind, we're going to do some things a little bit differently in terms of just developing an inexact first order proximal gradient type algorithm, and then use that as the basis for a second order method that can also use inexact proximal gradient calculations. Okay, so that's sort of the overall outline for today's talk. Of course, if anybody has any questions along the way, I'm fine if you want to just interrupt and feel free to ask. Okay, so a little bit more of an introduction. The problems that we're going to be focusing on are a pretty typical form where you're minimizing the sum of two functions. The one function f is going to always be assumed to be sort of, in some sense, the nice function. And by that, I mean it's always assumed to be differentiable. And in some cases, we'll have to assume it's, in fact, it's gradient. It's maybe Lipschitz continuous. And often, there are certain parts of our work that does not require convexity, but for simplicity and so I can just talk about everything that we've done, we will be assuming that the function f is also convex. Okay, so we know some common problems, functions like this. Our example come up in binary classification and when you're doing linear regression, things like that. Okay. The second function, the R function, that's typically the R for regularizer. So this is the one that for a lot of modern problems is not necessarily differentiable. And we'll focus on the case where that function is convex, but not necessarily differentiable. So it may be non-smooth, right? And I already mentioned the L1 as a case here, L1 function. But most of today's talk, most of it is going to focus on the group case. So where the regularizer is defined here, where you have, and for today's talk, you can just always think here of P as being equal to 2 if you want. But basically, it's the two norms of subcomponents of the vector x, where the subcomponents are determined by these groups gi. Okay, so we're going to have the variables are going to be divided up into groups. And then we look at the subvector of our optimization variable x. We look at it over these different groups. We look at that subvector components corresponding to those groups. You take their, say, 2 norm, sum them up, and that gives us an example of a group norm. Okay. And again, different parts of the talk, we're going to start out assuming these groups are not overlapping. And then later on, we'll talk about what we do when they're overlapping. And that's when things get a little bit more complicated. Okay. And there are some the most common examples where this group sparsity comes in, or examples down below where we talk about problems where covariates are coming in different groups. And there are problems in gene therapy, gene regulation, stuff like that, that are examples. And then the second one that I want to talk a little bit more about is just, I'd say the theme in modeling over the years has been to develop models that are now becoming more increasingly complex. And probably that's because for a long time we couldn't really handle functions that weren't convex very well. We weren't able to develop maybe reliable algorithms. And I would say that that's also, I believe, will be true in terms of the modeling aspects related to the regularizers. So as time has gone on, we started only with just the L2 norm typically, things like that, and then developed a lot of efficient algorithms for L1. And as time goes on and we're able to handle these regularizers better and more efficiently, people tend to develop more, in some sense, complicated algorithms, but ones that can be better for the applications in hand. Okay, so this is another place where these group regularizers may be coming in for particular applications when you have some reason to believe that there's some reason that certain variables should be grouped together. Okay, and there are some examples of this where people see that they can get improved accuracy, but also perhaps as important is the models that you get from using these regularizers can be easier to interpret. So these are problems we're going to be looking at. F plus R. F is the nice differentiable function, and R is typically non-smooth, but at least convex. All right, so in the title, and as I already discussed, we're going to look at algorithms that are sometimes called reduced space algorithms, and they use this idea of subspace acceleration that was in the title and that I just briefly mentioned earlier. Okay, so to be able to make sure we're on the same page about really what are reduced space or reduced subspace algorithms, let me just take a step back for a second here and let's just talk about a simpler problem for a minute, where we're minimizing a function f, say subject to, let's just say, non-negativity bounds on the variables. Okay, so the problem could look something like this, where let's say this is x1 and x2 variables, and perhaps the solution to the problem is here. Let's call it x star is the solution. Let it be the solution to this problem. So we know lots of algorithms for solving problems of this type, okay? And all of the algorithms will generate iterates that perhaps start at some initial iterate x0, and they are going to generate a sequence of iterates that are going to converge to x star somehow, okay? And here is one way in which the sequence of iterates from some algorithm could converge in the limit to x star, something like that, okay? And that's fine, but in terms of trying to develop some very efficient algorithms that can scale up to very many variables, I would argue that algorithms that can generate iterates that look more like this, okay, identify the components of x that are 0 and then converge, and then converge along that axis. So let me draw that in. And then converge along that axis in this way can be much more efficient. Okay, so I'm just saying that there are two potential ways iterates from an algorithm can converge to that solution x star. It can just kind of converge in some sense from the interior of the feasible region. Okay, because remember our x's are not negative. Or it's also possible, like the blue dots, to identify somewhat early in the optimization process which of the variables are equal to 0 at the solution. And right in this example here, the solution has x1 equal to 0, and you can see that the blue dot identifies that x1 is equal to 0 relatively early in optimization process, and from there you can converge along that axis. Okay. Now, why is this important? Well, in a two-dimensional example like this is not particularly, it doesn't really matter much between the red and the blue dots. But if you have a problem that has, say hundreds of thousands or millions, tens of millions of variables, and if at the solution that you're trying to compute, the vast majority of the components of x star, so assume that the vast majority of these components are 0, well, if you can identify that those are 0 relatively quickly, then really what you're effectively doing at that point is reducing the size of the optimization problem just to the variables that are non-zero, the ones that are allowed to actually change, okay? And if you only have, say, in the extreme case, maybe a few hundred variables that are non-zero at the solution, but in that case, even if you have 1 million variables total, if you only have a few hundred that are non-zero, then you're really effectively solving a very low dimensional problem. And that's where things can become much, much more efficient. Okay, so this is a very simple example. Algorithms that are designed for this type of problem, bound-constrained functions, have been developed for a while that have sort of this, sometimes called subspace acceleration. And the subspace is really referring to the fact that you're trying to identify which variables are 0 and then try to minimize along that technically affine space. Okay, so that's the basic idea of the basic idea here is to try to get information about the solution early on in the optimization process, as early as you can, in order to be able to reduce the size of the space in which we really need to be doing the optimization. And that can have lots of positive effects in terms of efficiency and so forth. Okay, now that simple, somewhat diversion there was to just talk about bound constraint problems. Okay, But those basic ideas are the same ideas that hold for problems that we're focusing on today. So minimizing f plus r. Okay, the same ideas hold there. Okay, if you think of r, for example, here, if you think of r of x as, say, for now, the L1, well, at the solution, some of these variables in x, some of them are going to be 0 and some are going to be not 0. And for lots of sparse types of problems that people study, at the solution, there could be very few non-zero components in the solution. And therefore, if we can, again, design algorithms that try to identify the 0 and non-zero patterns pretty quickly and efficiently, then we can design algorithms that effectively are solving very low-dimensional subspace, low-dimensional optimization problems in those subspaces. Okay, so the general then recipe that I have in this top of the slide here is just really getting us to start to formalize the general principles when you're designing these reduced space algorithms for problems in general of this type, f plus r. Right? And we're assuming that R is some kind of sparsity inducing regularizer. So there's going to be some either variables or blocks of variables of X that are going to be 0 at the solution. Okay, and the two main components in this sort of general recipe is, first of all, you need sometimes what's called a swapping strategy. So we are trying to predict which variables or groups of variables are 0 and which variables or groups of variables are non-zero. Well, you're not going to always get that right. So we need, at the beginning, we need to design some kind of strategy that lets us try to estimate which ones are 0 and non-zero. And if we make a wrong choice, as we're still moving along the optimization algorithm, we need to be able to essentially update our strategy. And to update the strategy means you're going to maybe take some that are predicted to be 0 and move them to some that are predicted to be non-zero and vice versa. Okay, so we need some kind of swapping strategy in these types of methods. And the other key component is the algorithm that we actually use to minimize over the non-zero variables, right? So even if I, at some point, identify correctly which are the 0 or non-zero variables or groups, even if I identify that completely correctly, I still need some good algorithm to minimize over those variables that are actually non-zero. I need to find out what are their optimal non-zero values. Okay, so that's the basic idea that goes into designing these algorithms. And if you want to prove anything about these algorithms, a common way for analyzing them is to make sure that you've designed your algorithm in a way that the objective function, f plus r, somehow gets sufficiently reduced over, from one iteration to the next. So as I go from, say, x sub k, the kth iteration, I go xk, the kth iterate, I somehow find an xk plus 1 that has reduced the objective function somehow sufficiently. Okay, that's the basic idea. As I comment on the bottom of this slide, though, if you really want to get really efficient algorithms that have fast local convergence properties, maybe good worst case complexity results, okay, well, you have to be more careful, but this is the basic idea. Okay, so I'm not going to spend much time on this slide, but let's just say that in general, there's been a ton of research on subspace methods, subspace accelerated methods, but the vast majority of these on this slide are for quite simple problems, most being bound constrained quadratic objective functions with simple bound constraints. Okay, there are some exceptions of interest here. For example, the ones I've highlighted in red, where here Steve Wright looked at a very general framework. But the general framework is so general that when you think about how to actually implement it for any particular choice of regularizer, things get pretty complicated. And although you're able to do it, and he was able to do it for the L1 case, when you think about how to apply his framework so it's actually implementable for the group L1 case, the group regularizers, it's not at all clear how to do it. Okay, and in fact, to this point, it's still kind of unknown how you can actually have an implementable algorithm in that setting. There's some other here by Kesker, Nosedal, Ostaprak, and Vector, but their work focuses on, again, the L1 case. And the last paper I'll mention here is by Zhang, Sun, and To, who were interested in some very similar things as we are, have been, but we're going to see that we've done things very differently. In some sense, the research they've done and what we have done is very complementary to each other. You'll see that our method outperforms theirs significantly on a certain large class of problems. And there's a complementary set of problems in which their method works significantly better than ours. Okay, and this all comes down essentially to the size of the data set relative to the size of the optimization variables. Okay, so very complementary in some sense, very different, but complementary in that sense. Okay, so what is this second order method that we've developed? So it's a second order method, and it's going to use subspace acceleration, as I've just discussed. And it's built upon, for now, exact computations of what's called the proximal gradient calculation. Okay, so again, we're going to focus on the problem F plus the group. Okay, we are going to assume for now that these groups are non-overlapping. Okay, so these sub-indices, these index sets GI, are assumed to be non-overlapping. Now, if you don't know the proximal gradient method, it's a very simple method. You have your kth iterate of your algorithm. You get your k plus first by adding to it what's called the proximal gradient step. And the proximal gradient step here is computed by solving a relatively simple optimization problem. Where this simple optimization problem, you can see it as, well, this is like a first order Taylor approximation. This is some sort of regularization added to the step. And then we have here explicitly the regularizer itself. Okay? So this is known as the proximal gradient step. And if you just use this iterative procedure here, under certain assumptions, the iterates will converge to a solution of your problem. One thing that I should mention is that this computation here depends on a parameter alpha k. Alpha k is called the proximal parameter. And in practice, of course, that's important to be chosen. For everything today, I'm just going to assume that that's chosen appropriately because everything we're doing in our research is not really contributing to that choice of alpha k. So we're just going to assume for this talk that it's as small as you need it to be. In practice, though, of course, you need some strategy for potentially updating that alpha k, but we're not doing anything in our research fancy there. We're just using some standard practices. Okay. Okay, so what is then the method that we've developed? So these are the main key components of the algorithm. So the first thing we do is we compute the proximal gradient step sk. That's the first part of the algorithm. Okay, so we compute that proximal gradient step. Then what we do is we define, by taking the norm of that step, we define this optimality measure chi k. Okay, by optimality measure, what I mean, just to be clear, is that this chi k will be equal to 0 if and only if our current iterate is actually already optimal. So you could think of the size of chi k, you could think of it as a measure of how close you are to optimality. Okay, now what we need to do, because we're trying to develop these subspace accelerated methods, is we have to somehow partition our variables up into these groups of variables, into those that we think are zero groups and those that we think are non-zero groups. Okay, so that's the main part of point 2 here. So how do we do that? Well, first let me just show you this picture, okay, to give you the idea. So let's focus on the left-hand picture for a minute. So I look at my xkth iterate, and I look at a corresponding to the group GI. Okay, and I look at it, and I want to know, do I think that vector, do I think, at the solution, do we think it's going to be 0 or a non-zero group? Okay, and in this picture, here is the origin, so here is 0. So the question is, do we think that this group associated with xk, do we think it's going to be 0 or non-zero at the solution? Well, the basic idea of how we decided in our work to do that is we create this ball, the blue ball here, around the origin, centered at the origin. And importantly, the size, the radius of that blue circle is given by this quantity here. And you can see that it looks at the gradient of the objective function, but restricted to a certain subset of variables. Those are the variables that we want to say. Basically what we're saying here is that this is like a measure of optimality in those variables that are non-zero. And I want to make sure if I'm going to predict that this x is going to be non-zero at a solution, I want to make sure that it's far enough away from zero, far enough away related to some optimality measure in that space of variables. Okay, so the basic idea is when we're forming which we think are the zero and non-zero groups, part of that decision is to be considered part of the non-zero variables, ones you're predicting to be non-zero. It's not just are you zero or not zero. That's not what we're doing. If you're going to be predicted to be non-zero, you have to be quote unquote far enough away from zero. And that far enough away from zero means you're outside of this blue circle, okay, with that particular radius. Okay, now this is really crucial to define things like this, because if you just go ahead and just define them based on those components that are zero and non-zero, well, then you start to run into issues because as you're approaching zero, the group norm is not differentiable there. And therefore, since it's not differentiable there, you're going to have all kinds of issues with proving convergence of anything. Numerically, you're going to also have a disaster because the gradients can be blowing up to infinity, and you're going to have terrible, terrible numerical performance. Okay, so we've tried all these things. We've tried modifications of other work we've done for the L1 case, just the standard L1 case, and they all fall apart when you start talking about the group case because things are inherently different because of the non-differentiability of the group norm at zero. Right? The fact that you have more than one variable in a group causes issues. Okay, so that's the basic idea of how we form this partition in step 2. We look at our variables and we look at those that are far enough away from zero, and those are the ones that we consider as part of this group. We call, it's just notation, but we call IKCG. Okay, CG because in those variables that are away from zero, we're going to apply what's called a Newton CG type method to try to use second derivative information to optimize over those non-zero variables. Okay, but that's how we get the zero and non-zero structure, okay, of the variables. Okay, so now after we've determined that partition of the variables, those that we think are zero and non-zero at a solution, we then go into step 3. And step 3 is now, well, I have this partition of the variables, some that we think are zero, some that we think are non-zero. Our next step is we're going to take action by either trying to optimize, minimize over the predicted zero variables, or we're going to take a step to minimize over the non-zero predicted variables. We're going to try to make progress in one or the other. And the way we choose which one to try to make progress in, which set of variables, is we look at our proximal gradient step, okay, that's SK here, and we look at it relative to the two different sets that we've defined up above. These are the ones that are predicted to be zero and non-zero. So if this inequality holds here, this is saying that the size of our step in our space of predicted to be non-zero variables is relatively large. So that measure of optimality is relatively large compared to these variables. So what do we do in that case? Well, we optimize over these variables that are being predicted to be non-zero. Okay, so these are these non-zero variables where everything is nice and differentiable, everything is good, so we can apply their standard, fairly standard techniques for minimizing an unconstrained function in those non-zero variables. What we do is we apply basically an iterative method to approximately solve a linear system. I'm not going to go into these details. If you're familiar with this, this is obvious. If you're not, just know that there is a fairly standard algorithm that's quite efficient for minimizing functions that are unconstrained optimization problems. Okay, and we're applying that in this context of the free variables. Okay. Well, once we do that in this, we get a step dk. That's the possible step we may take in these variables, right? In these variables that are non-zero. Okay, but we're going to actually now modify things a little bit. Okay, the way we're going to modify things is by saying, okay, this is the step. This dk step is a step that we're predicting by approximately solving our Newton system is potentially a good step to take. But we have to be careful because we also know that, well, we may be wrong, right? Our prediction of zero and non-zero variables may not always be right. It may be wrong early on. Okay, so what do we do? Well, let's look at this picture on the right this time. So here's an instance where we have our current xk for this group. We have this blue circle again, which is the circle outside of which we know xk lies. We talked about that previously. We then take a fraction of that, and that's this red one here. We take a fraction of the radius of the blue circle, and that becomes our red circle. And then what we do is we look at the step dk that we've computed. Okay, so here's an example of a step dk. All right, xk, and this is the step dk. And notice that that step dk intersects this red circle. So notice, though, that although xk is being predicted to be non-zero, it is pointing very much close to 0. It's pointing in the direction of 0. And that may be an indication that your prediction was actually wrong, that although you predicted xk to be non-zero at the solution, those variables to be non-zero at a solution, it's possible that maybe your prediction is wrong. So what we do is, this is the full step, this is x plus dk, is, well, anytime that step, like here, intersects the red circle, we take all of these points, and when we do a backtracking line search, so what we do is we project those points back to the origin. So if we backtrack to here, we project, we keep backtracking, we project. As we're searching along this direction dk, as we're searching for a better point, a point that reduces our objective function, instead of using these points themselves, we project all of them back to the origin. It's only once we leave this red circle, as we're searching, and we leave the red circle, so it's these points, those we don't project anymore to 0. Okay, so this is, if you're familiar with backtracking line search type methods, this is a modification of it that uses something like projections. Okay, but completely motivated by the fact that we understand that we are trying to identify the zero non-zero structure, and that, well, this picture that we've drawn here is an example where, well, maybe, although we're predicting this to be non-zero, maybe it actually is supposed to be 0, because when we look along that direction dk, it points, quote unquote, relatively close to 0. The picture on the left is a little bit different, right? We have the same xk, but notice in this example, I've assumed that the step points away from the origin. Okay, so it's outside of the red circle. Okay, in that case, when I say away from the origin, technically it's at first going closer to the origin, but when I say away, I just mean outside of the red circle. In this case, we would just do a standard backtracking line search without any projections. Okay, so when your step intersects the red circle, you do a projected, that's this side, you do a projected search. When the step does not intersect the red circle, like on this side, then you just do a standard backtracking line search. Okay? So that is everything that we do in this case here, right? When we look at this, we compare our measures of optimality in the 0, those predicted to be 0 versus those predicted to be non-zero. And if the ones predicted to be non-zero have a larger measure of optimality measure, then we compute an approximate Newton CG step. Then we perform this modified projection like I just described, and that's it. Okay. If this inequality fails to hold, then it's telling you, if it fails to hold, that, well, that this is a larger quantity. So when it fails, this is a larger quantity, which means that, well, those correspond to the groups of variables that you think are supposed to be 0 at the solution. So in that case, what we do is we just perform a standard backtracking search along the negative proximal gradient step restricted to those variables that are predicted to be 0. Okay, so this else, in many ways, looks like a standard proximal gradient algorithm, but restricted to those variables that you're predicting to be 0. Whereas if you go into the if, this is very different. This is including second derivative information here. Okay, this h, I've just said, is the Newton system, but this h, k, is the second derivative matrix of the objective function restricted to just the variables that are predicted to be non-zero. Okay. Okay, so again, just a quick overview then of this method is we compute the proximal gradient step, we compute an optimality measure. We use what we just described on the next slide to divide the variables into the zero and non-zero variables. We then look at the size of the proximal gradient step over the zero and non-zero variables, and depending on which one is larger, we take action. We either compute a reduced space Newton CG step with a modified backtracking line search as I just described, or in the else case, we just perform a very simple basic backtracking line search along the negative proximal gradient direction restricted to those variables.
Can I ask a question here?
Yeah, go ahead.
So in your algorithm, you somehow need to determine a partition of the set, right? How do you get to the partition?
Yeah, so it's what we basically do is we have actually a recursive way of trying to get it. So we look at those blocks of variables that are farthest away from zero, and we include that in the set. If it satisfies this property. Okay. If it does, then what we do is we try to increase the size of these variables by looking at the next group of variables that's farthest away from zero. And we potentially include that, and we try and we see if those variables also satisfy this condition that we need. If it doesn't, then we remove the one we just added and we go back to what we had. If it does satisfy this property that we need, then we then proceed to add the next group of variables that's the next farthest away from zero. And we keep doing this until, well, this has to terminate one way or another, because either you eventually add all of the groups and they all satisfy this property, and then you have your partition, or at some point it fails, in which you go back to the previous one in this iterative process, and you use that as your set here of the predicted to be non-zero variables.
So that means because this circle also depend on the partition, right? Like
Yeah.
it acts as a gradient restrict on that set.
Yep.
So it's like every iteration you have some initial partition, then you check those properties, and you have some recursive update to this partition. Then
Yeah.
you have
Yeah.
properties.
Yeah, exactly. What I attempted to just describe is that iterative process in its simplest way. So you start with the one farthest away from zero, and you start with the one that's farthest away from zero, and you let that group only be part of that set, and you check to see if this is satisfied. If it is satisfied, then you take the next group that's farthest away from zero, and you include that, you add that to this set, and you check this condition. And you keep checking that condition until it fails, and then you go back to that previous iteration of this iterative process, and then you use that as your set.
Oh, I see.
Yeah, so it's a great question. So you need to somehow get this partition to satisfy. It looks like it's defined sort of implicitly in the definition. It kind of is, which is why we use a recursive way of getting it.
Mm-hmm. Thanks.
Yeah, no problem. Good question. Okay, so what can we prove then for this overall algorithm? Well, under some pretty standard assumptions up above, we can prove a worst case complexity result where if you ask the question, how many iterations does it take until our optimality measure chi is below epsilon for a chosen epsilon? So you give me epsilon, and what's the maximum number of iterations until I know my algorithm will make its optimality measure below that epsilon that you give me? The answer is it'll take O of epsilon to the minus 2 plus P, okay? P is some user-defined parameter that I've not gone into in detail yet, and I'm not going to. It's in the paper, but the P is related to the size of that radius that we talked about earlier. I've simplified things a little bit for this talk, but you can integrate into the definition of that circle, that projection circle. There's a quantity that has a user-defined parameter. That parameter just has to be anywhere on 0 to infinity. But other than that, there's no restrictions. Okay. Now, from this result, then what you can, or this result, I should say, follows because we can prove that for each iteration of our method, this is the value of our objective function at the kth iterate. Once I use our algorithm and we generate xk plus 1, the objective function there, we know that the amount of decrease is going to be proportional to chi to the 2 plus p. Okay, so this is a key result we need to prove. We proved it, and once you have that, then it's pretty straightforward to be able to prove this worst case complexity result. Okay, so a couple comments about this result is that as P, this P up here, converges to 0, this is converging to O of epsilon to the -2. And this is exactly the result you get from the standard proximal gradient method. Okay, so no fancy second order acceleration or anything. It's standard simple proximal gradient. In the setting we're talking about, you'll get epsilon to the -2. And notice that that's what you recover as you take this parameter P and you let it converge to 0. Okay, so it's sort of interesting that you recover that, but it shows you that you do, at least in terms of a worst case complexity result, you pay a price for being able to get second derivative information into the method. You pay a price in terms of the worst case complexity result because of this P that appears. Also, a little bit different and definitely worth mentioning is that although we say this is O of epsilon to the -2 plus P, these big O's always have constants in them, and those constants can be better or worse, and those constants, if they're better or worse, can have a big impact on the performance of algorithms. So in contrast to the proximal gradient method, our constant that's hidden in this big O, that constant does depend on the number of groups. Okay, so our constant gets worse as the number of groups increase. Okay, so in any case, though, this is still only a worst case complexity result. I'll just say that in terms of comparing numerically how our method performs versus proximal gradient, our method is significantly better essentially across the board. Okay. Local convergence result about our algorithm very quickly. We have, under certain, again, assumptions that our method, the iterates for our method will converge superlinearly. With slightly stronger assumptions on F, it'll actually converge quadratically. And also about how accurately we solve our linear system that I wrote down before during the, we talked about using Newton's CG algorithm. So it depends on some other things, but those can all be easily implemented. So I would just, the takeaway message is that if you want, this algorithm can be superlinearly or even quadratically convergent if you want that. Okay, and typically we do, because typically they do perform better in practice. A last thing is our algorithm we are also able to prove has a support identification result. So this support identification result is all, if I go back for a second, is similar to this picture, right? Does our algorithm create iterates that look like these red ones and that converge from the interior? Or do they look like the blue ones, that they will identify which x's are 0 and non-zero at the solution relatively early, and then from there you can just converge along the non-zero variables? Okay, well, that's really what this local convergence, the support identification result is about. It says that for sufficiently large iteration k, our algorithm will generate an xk that correctly identifies the 0 and non-zero group structure. It is worth saying, though, that to get that result, we do need to make a non-degeneracy assumption, but these non-degeneracy assumptions are fairly standard throughout optimization. Without them, it's very difficult, sometimes impossible, to prove any kind of support identification result. It's at least difficult, not impossible in some cases. Okay, so quickly about numerical results. I'll just say that we did a bunch of testing on fairly standard data, binary classification problems and regression problems from libsvm. We tried multiple sparsity levels. We tried multiple ways of defining the groups. So these are all sort of synthetically created groups. And we compared our method against several algorithms, against FISTA, so that's a fast or a Nesterov accelerated type of proximal gradient type method. We have Lasso, which is a method that uses upper bounding majorization models as a subproblem during each iteration of the method. PNOPT is a method by Michael Saunders et al. Out of Stanford, where they're using second derivatives like we are, but in a very different way. They're using them to define the subproblem that are used explicitly. It's sort of an extension of the proximal gradient subproblem. And then there's this method, SSNAL, stands for semi-smooth Newton method, that uses an augmented Lagrangian function. And that one's going to be interesting as we go through these quickly through these numerical results. Okay, so here are the numerical results. This table, these bar charts have along the x-axis, there's a bar. Let me zoom in on one for a minute. You'll see there's a bar here. All these blue bars point up, and you'll see there's one red bar that points down. And each data set that we tested, each problem we tested, has a bar associated with it. Okay, and for this particular graph, we're looking at computational time. So a blue bar, so one pointing upwards, means that our algorithm, the proposed algorithm, did better on that problem, that test problem, in terms of computational time. If you have a downward pointing bar, then the competing algorithm, in this case, Vista, did better than us. And you can see that a more Nesterov accelerated basic proximal gradient method is nowhere close to how well we do in terms of these data sets and the training of these models. Okay, nowhere near. There are other algorithms. You'll see that GG Lasso is here. You'll see that the PNOPT algorithm is here, and you'll see with two different versions of PNOPT here, two that they have in their software. We tried them both, and you can see that they're almost all blue pointing upwards, meaning that we do better. Okay. The one that's a little bit more interesting is SSNAL. So that's the semi-smooth Newton method based on augmented Lagrangian. And you see that we still do significantly better in general. But there are these problems that we don't do as well on. Okay? And after we looked a bit more into the problems and also spoke a bit with the authors of the paper associated with this algorithm, we realized that the main issue, well, it's not really an issue, but the main difference is that really we do better on complementary problems. And once you look more closely at all these data sets, what you would see, okay, is that these test problems are all problems where the size of the data set is significantly larger than the number of variables. So lots of data, okay? These problems over here happen to be problems where you have, quote unquote, little data. So you either have little data, but it's at least little relative to the number of optimization variables, okay? And the reason that this turns out, after we look more into it, is that really it's because their method is more of a dual approach. So it works on a dual problem. And in that sense, these two methods are very complementary, as I mentioned at the beginning. Okay, so if you have problems where the number of variables where the data is significantly larger than the number of optimization variables, then you absolutely, definitely should use our method, no doubt. If you have a problem where the number of variables are significantly, well, let me say it the other way around, where there's less data than variables, so you don't have that much data maybe, then we would definitely recommend you should use their method in that setting. Okay, we do perform relatively comparable, but their method does tend to perform a little bit better. So we would just, in that setting, recommend you use their algorithm. Okay. All right, so this is the numerical results that I already just discussed. I'm going to leave it at that. Okay, so I think I have just a couple minutes. Is that right?
I think 10 minutes.
Oh, 10 minutes. Okay, well, then I can even say more. So, okay, so what I've discussed so far is, again, assuming that you can do the exact computation of the proximal gradient step. So what happens if we want to do problems where the regularizer is one where you cannot compute the exact proximal gradient step? Well, then we need to understand inexact proximal gradient algorithms and their computation. Okay. Now I'm going to go over parts of this very quickly. Some stuff skip over a little bit, but I want to focus on the main ideas here. So what is then an inexact proximal gradient method? Well, you'll see that you have your current iterate xk is here. You add to an inexact proximal gradient step. where the inexact proximal gradient step approximates the solution to our standard proximal gradient step. So you just have to solve this subproblem inexactly. Now, there are ways, different types of conditions that we could use to say exactly what we mean by it's an approximate solution to this problem. What we focus on for multiple good reasons is we focus on what are called adaptive conditions in our work. Okay? By adaptive, what we really mean is that we've developed two conditions. Okay? One of them is similar to some work by Lee and Wright, although a little bit different, and one that's completely new as far as we know. But two examples of adaptive conditions. Okay? What do I mean by adaptive? What I mean is that these conditions involve quantities that depend on local information of the algorithm. So as you're iterating along, you're going to use information about where you are in the search space to decide how accurately you need to solve this problem. Okay? In comparison, some people have considered absolute conditions, where you see that it involves the iteration, k. So that this tolerance that you're allowed on the subproblem solutions depends on the iteration k, so it's predetermined, right? It doesn't depend on where you are in the search space at any given point. It all depends on the iteration k. So we don't like those. Those don't tend to work as well in practice, although you can, of course, prove things about them. We care about more conditions like this that depend on things like local information, like the approximate proximal gradient step. Okay? All right, so we propose two different adaptive conditions. I will say that, notice that, for example, option 1 here depends on sk, which is the exact proximal gradient step. Okay, now that might not sound like it makes any sense because, well, we're trying to avoid the computation of the exact proximal gradient step because it's not directly computable. Okay, but what we show in our work is that, well, you don't have to compute the step sk, and yet you can still know whether when you terminate your approximate solution to this problem, you can still do it in a way where you know this condition will hold for certainty, even though you haven't computed sk. Okay, and the way we do it is we use a primal dual formulation, and by using duality theory, we can guarantee that when we terminate our algorithm, these conditions are satisfied. Okay? Okay. All right. What have we done? Well, when we're looking, the reason why we use these options, right? When I say these options, I'm talking about, this option here, okay? These different options. The reason why I use those options is because what we can then prove for these inexact proximal gradient steps is that we can prove each iteration of the algorithm has a decrease of this type. Notice that the objective function at the kth iterate, objective function at the k plus first iterate, the decrease is proportional to chi squared. If I went back in the talk, you would see that this inequality is the exact same inequality that we were able to prove for our second derivative method based on the exact proximal gradient step. So since this was the goal then, when we reinvestigated these inexact proximal gradient steps, was to prove an inequality like this for these inexact ones, because we knew that we could then integrate this inexact computation into our second derivative methods. Okay. Now, I'm not going to go into the details of this, but the bottom line is these options for terminating the subproblem solver were designed in a way to make sure that we actually get descent directions for the objective so that we can actually make sure that we decrease the objective function proportional to that chi-squared measure. Okay, that was the whole goal, and we were able to do that. Okay, these are some details, but I don't want to get into the details of all these things. But these were constructed so that we would get exactly this inequality. Okay, what can you then prove? Well, everything we hope to get for this so that we can integrate this inexactness into our second derivative method, we were able to get. So for example, notice that this is an epsilon of -2. It's the same result for the exact proximal gradient method, but remember ours is inexact. Okay, and also, which is nice, we can prove that for iterations k, k sufficiently large, our inexact proximal gradient step eventually accepts the unit step size within the algorithm, meaning that no backtracking is required. Eventually, we just accept this inexact proximal gradient step. And that's always a good thing in optimization if you can accept the unit step for multiple reasons. Efficiency is one of them. But also in our case, we want to make sure later that we can try to incorporate a second derivative method with subspace acceleration. We want to be able to identify the zero and non-zero structure of the problem. Okay, so accepting the unit step is often a good thing. Okay, there's some numerical results, so I'm not going to go into these in detail. I'm just going to say that we tested our options, and the two options that we've developed tend to be very insensitive to parameter selection. So all of these are two options. We have two different options, option 1 and option 2. Okay, option 1 and option 2. And there's another method that we tested against, which we call option 3, which is not our option. It's one that's based on the absolute kind of stopping condition. And what you find is that these adaptive conditions, this is one of the reasons why we like them, are very insensitive to the choice of parameters. Okay, so that's a good thing. Okay, I'm not going to get in much detail, but that's the main point of me putting just these numerical results in there. Okay, so this means, practically speaking, that you probably should prefer adaptive conditions versus these absolute stopping conditions because they tend to perform well across a large scope of your parameters. So over a larger selection of test problems, they should perform well without having to do a ton of fine-tuning. And fine-tuning can be bad. Okay, the last part is, well, I think it's just 1 or 2 slides, is, well, now that we understand better the inexact proximal gradient algorithm that we developed in these conditions that were specifically used to get the decrease we needed, or that we actually had and used in our previously defined algorithm. So the decrease we get in this algorithm, we now have shown that when we do the inexact computation using our termination option 1 and option 2, we get the same decrease. Well, now we can just combine these two basically together to get a second order method, like the one I first described, but use it when we're doing inexact proximal gradient calculations. Okay, and I think I just have one slide. Yeah, one slide about it is just, well, when you take and do that, does it work? Right? Can we just now use this inexact computation to get within our second derivative method with subspace acceleration that I talked about earlier? And the answer is, does it work? Well, the global convergence is pretty straightforward for the reasons I said. Okay, is that we get the same decrease every iteration in our method. So that's pretty straightforward. However, the local convergence is not straightforward. It comes down a lot to whether you identify the actual support, right? So can you, in finitely many iterations, determine which blocks are 0 and which blocks are non-zero? Okay. Now, a result like that is known for the exact proximal gradient step. But for inexact proximal gradient steps, it's much more complicated, much more difficult. It actually required us to develop our own subproblem solver that allows us to get this result. So it sort of required that additional effort on our part. We're still working on this. It's not published yet, but we're still working on this. Okay, and I'll just say that the preliminary numerical testing for this inexact secondary method using overlapping group regularizers is so far performing quite well, but we have to do a lot more testing. Okay, and then I'll finish with this slide, which is hopefully, for those interested in optimization, hopefully we'll get a chance to see you at this year at ICC Opt. We're holding it jointly with the MOPTA conference. It's going to be at Lehigh. Here are the dates, and there's a website that you can easily find it to look into it if you're interested in trying to come to the conference. Okay, that's it. Thank you very much.
Okay, thanks a lot for the very nice talk, very clear.
Okay, good.